Hello, everyone. We're going to get started with this week's Organic Chemistry 2 weekly review. So this last unit, we have a couple reactions, mainly aromatic reactions, and a few chapters left. One of the first things that we're going to talk about is molecular orbital theory. And essentially, that has to do with a little bit of resonance and a word called conjugation. So let me draw that up. Okay, so we have the structure is called 1,3 diene, 1,3 dash diene, and its nomenclature is this because there's a double bond on the one carbon as well as the third carbon, and of course on the second and fourth, but we only number from the first carbon that the double bond is on. And the di, di is for two double bonds, and the E is to call out the double bond rather than single bond. Okay. All right, so a couple of other terms we have to know is HOMO, which stands for highest occupied molecular orbital, and LUMO, which is the lowest unoccupied molecular orbital. And those will come into play a little while later. Just a reminder, we are going over the molecular orbital theory, which is important in chapter 15, heading into our aromatic chapter. Okay, a couple other things to note. So let's talk about conjugation before we move on. So each double bond contains these little pi orbitals, because that's where our pi bonds are gonna slot into. Okay, so remember that anytime we have resonance, those lone pairs can occupy a pi orbital because they are delocalized and can freely move around. And that's exactly what's happening here. All of these electrons on these double bonded carbons have all contained pi orbitals. For example, if we drew something like this, we would draw only pi orbitals on these two carbons and these two, and not these two because they cannot resonate onto this without a charge. But if I added a charge, let's say I added a negative charge, then this carbon will also be included in the pi system. Okay? So that's just something to keep in mind on how conjugation works. Conjugation is a very similar concept to resonance. Since you guys already know how resonance works, this concept should be fairly easy. Now we're gonna get into the bulk of what molecular orbital theory is, And again, we're going to use our model, molecule 1,3-diene, okay? And I want you guys to understand a couple main things that you want to figure out when solving the molecular orbital theory is, first of all, how many carbons are in conjugation. So in this case, it's going to be 4 carbons in conjugation. And then how many total pi electrons are there? Okay, and the answer would be 8 pi electrons. Oh, I'm sorry. It should be 4 pi. Okay, and the reason why it's 4 pi is each double bond contains 2 pi electrons. So 2 double bonds means 4 pi electrons. Okay, so let's see what the answer would be if we were to look at our second structure. We have 1, 2, 3, 4 carbons that have the pi orbitals, but this resonance, this charge, is allowing for a 5th carbon to participate in this conjugation system, or resonance system. Okay, so the answer here would be 5 carbons in conjugation. And then, so does anyone know how many pi electrons? Okay, so if a double bond is 2 pi electrons, and negative charge is going to be also 2 pi electrons. So altogether, 2 double bonds and 1 negative charge, we have 6 pi electrons. So let's write that down. Okay. My bad, not electrons. Okay, and then just to give you guys kind of like a key, we have a double bond, a negative charge, a positive charge, a radical, and a triple bond. So a double bond is 2 pi electrons, same as a negative charge. Okay, a positive charge is going to be 0 pi electrons. There's no electrons there. A radical is a single pi electron, and a triple bond contains 2 double bonds, so it's going to be 4 pi electrons. Okay, so this is kind of like a legend for you guys to understand, or rather a key to decipher any given molecule. All right, so like I said, any given structure, we have to figure out these two information, because then we can figure out the rest of the problem. So however many carbons there are is however many energy levels you are going to draw. So because there are 4, actually I can do the 5. Let me do the 4 carbon first. So let's start with the 4 carbons. Okay. And I'm going to label this 1, 2, 3, 4. And I'm also realize I can zoom in so I can make it easier for you guys. Okay. So again, let me do that. Again, remember these pi orbitals. With this structure, we have 4 pi orbitals because 1 at every double bond, and there's no charges. So it should usually match up with however many carbons are in conjugation. So I'm going to draw the 4 orbitals now. I'm going to choose to draw it in red. And I'm going to draw it as evenly as possible. Oh, get rid of that. Okay, so it does take a little bit of time, but I believe you don't actually have to draw the molecular orbital. You have to use the orbital to actually answer questions. So don't worry about this part. Just understand how the theory works and where everything is coming from. All right, there we go. So now that we have that, one last bit of information or a couple of things. First, each energy level is also going to have a orbital next to it. Okay, and just a review from general chemistry, each orbital can only contain 2 electrons. Okay, and we can actually go ahead and fill in our electrons, but before we get to that, I am going to also talk about nodes real quick. And I'm going to do that in green. So nodes are separations of charges where it alternates. And the formula for nodes is fairly simple. It's simply n minus 1. Okay, so don't get this confused by the NMR formula, n plus 1, neighboring hydrogens plus 1. This is n, in this case, stands for energy level. So I'm going to go through all this. So 1 minus 1 equals 0 nodes, 2 minus 1, 1, 3 minus 1 is 2. You just subtract 1 from each energy level, and that should tell you how many nodes per energy level. And nodes, like I said, are changes in the charge, or where the electron is. Okay, and we are going to showcase that through dotted lines. So 0 nodes means 0 changes in the charge. Okay, so we're going to fill this in. So 0 changes means we're going to fill in all the top. We're going to shade in all the top. Okay, 1 node means we have to draw a dotted line in the most equal position of the pi orbitals. So I see 4, and I'm going to divide that by 2, which gives me 2 and 2. So I'm going to draw a dotted line right there. More or less a dotted line. 2 dotted lines, 2 nodes. I'm going to separate it 1, 2, 1. 3 is going to be between all of them. 1, 1, 1. Okay, and now all we have to do is fill in the nodes. So I'm going to shade in the tops, and then after the node, I'm going to switch over to the bottom. Okay, so the third energy level, I'm going to switch, keep, and then switch again. Fourth energy level, switch, switch, and switch. Okay. The last energy level, you're pretty much alternating for every single orbital, and then the first energy level, everything should be on the same line or the same side. Okay. And last but not least, we are going to fill in these orbitals, and that's where our pi electron comes in. We have a total of 4 pi electrons, and each orbital can only occupy 2 at a time. So I'm going to draw in our arrows because that's how we indicate electrons, one up, one down, to show the spin of each one. Okay, and we are done for this problem, except one last thing is the Homo and Lumo part. We have to assign one of these orbitals Homo and one of these orbitals Lumo. Okay, and let's review what Homo and Lumo means. Highest occupied molecular orbital. So the word occupied is first important. So energy level 1 and 2 are occupied by electrons. And between 1 and 2, 2 is obviously higher. So it's going to be considered the Homo orbital. Orbital is within the word, so it's energy level 2 is Homo, and energy level 3 is going to be Lumo because it's the lowest unoccupied molecular orbital. Okay, we have 4 molecular orbitals, 3 and 4 are unoccupied, and 3 is the least or lowest orbital that's unoccupied. All right, I hope that makes sense. I'm not going to draw in all the nodes for the rest of these, but I am going to draw the electrons for the second structure. So I'm going to draw 5 lines this time because of 5 carbons in conjugation. And actually, instead of a negative charge, I'm going to do a radical because I think that's important. Okay, so that obviously changes this from 6 to 5 because we have 2 double bonds and 1 single electron. So 5 electrons means 1 here, 2, 3, 4, 5. Okay, so any guesses on what Homo and Lumo would be? Okay, so remember, Homo is highest occupied molecular orbital. Okay, so occupied does not mean fully occupied. It could mean a single electron is considered occupied. So energy level 3 is actually our Homo, and energy level 4 is our Lumo. So don't get tripped up and confused and accidentally write this as Homo and this as Lumo. Even if it's a single electron, it's still going to be considered occupied. All right? Okay. So there you have it. That is molecular orbital theory. A couple of other things that I wanted to talk about, especially in chapter 15, is Diols-Alder. And chapter 16 is when we get into aromaticity and aromatic compounds and its reactions. Okay? So I have time to start on Diels-Alders, and then we'll finish up Diels-Alders and get started on chapter 16 next week. And talking about all about aromaticity and how to identify it. And then the following weeks we'll go over all the reactions. Okay? So I'm going to draw a dotted line. All right. So for Dow's alders, let me write her name down. Okay. We have two important names. One is called diene, the other is called dienophile. Okay. So diene, so each of these have a parent structure, and before we draw that, I'm gonna define what both of these mean. Diene just simply means two double bonds, and dienophile means two double bond loving. Remember, phile means loving. So one is going to love the other. In other words, in chemistry words, they're going to attract to each other and create one big compound. Okay, and now I'm going to draw the parent structure that you should always have some sort of starting point. So your diene should always be in a S-cis fashion. Okay, these double bonds are facing the same direction, so that's why it makes it cis. And then we always have a plus between diene and dienophile. And the parent structure is simply going to be a double bond. Okay. Now the product of the parent structure, when combined, is going to look like a cyclohexane with a double bond at that location. Okay. And the reason why, and let me actually zoom in. The reason why, oh, this got moved over, but I don't think it matters. Okay. So I have to show arrows to make sure you guys understand where everything is coming from. This double bond is creating it's completing the ring by making itself into a bond. This double bond is getting shifted over to where the product is. And then these last two bonds are coming from our dienophile. This one is completing the ring right here. And then this right one is going to just slot into here. Okay? So with all of those extra bonds, it should create 6 bonds in a cyclohexane as well as this double bond right here. Okay, so that is the parent structure. Okay. And that's all I'm going to get into today. There's a little bit more that you have to deal with Diols alders before you begin to practice problems, mainly stereochemistry and different groups on our dienophile, such as endo and exo. Okay, and we'll get into all that next week with lots of example problems. This should be a fairly easier concept, and a lot of people quickly get it. But after that, we will get into aromaticity and then its reactions. So thanks for joining us, and see you guys next week.